This
I think it
conference will
started
now
now.
be recorded.
So my video is now started, and I'll copy that afterwards into the folder. And by the way, talking about the folders, if you let me just find it for you. Yeah, if you want to know more about presentations which as UK Acoustics Network run, they all saved in on the Google Drive in here. And I'll send you the link to this Google Drive. But this link will also appear on the website of our network. I'll share this with you everywhere. So here you go. So you can get to it. And my presentation will be in this folder, together with some papers and MATLAB code, which I will leave for you to play with and to read. Okay, the outline of my presentation. First, don't be offended, but I'll tell you a little bit about basic acoustics, just to make sure that we all understand what quantities we're dealing with. So then I'll talk about key non-acoustical parameters and their influence on acoustical properties of porous media. And then I talk to you about test methods, then talk about models and find out how these models actually work. And then we have a question and answer session. My presentation also contains a appendix, which basically explains some smart ways for enhancing sound absorption in porous media. Okay, so any questions so far? Okay, you're quiet. So let's talk about basic acoustics first. So when we deal with acoustics of porous media or other types of acoustics applications, we normally talk about sound pressure. And this sound pressure, we call it P. It is a function of time, T, frequency, omega, and space, X. Usually, we decompose any complex sounds, like my speech, for example, into harmonics, and we deal with each spectral harmonic separately. So for a total sound, for a harmonic sound wave, the total sound pressure in this case will be a product of the amplitude or spectral amplitude and some exponential term which contains all these bits. It also contains a value called k, and this k is a wave number. Here I will use the little character called I, and I square root of -1, which is an imaginary one, just to show that we always deal, or usually deal with complex quantities. So sound pressure and other quantities associated with that tend to be complex. Okay, so in this case, what important in the previous expression is wave number. And wave number is important because by definition, wave number is the frequency of sound divided by the sound speed. When we talk about sound speed in air, it's a real quantity. It's probably 340 meters per second. But in acoustic materials, or like porous media, it is a usually complex quantity. It contains real part and imaginary part. The real part, it basically tells us how fast sound wave travels. An imaginary part tells us how fast sound wave attenuates. And obviously this has a unit, which is 1 divided by a meter, and the reason why, because multiply by the distance sound wave propagates. Okay. So also we like to define another property, which is called acoustic velocity, which is basically normal derivative of sound pressure taken on the surface, usually, of the porous medium. And here we've got a density of fluid, normally air, and we've got a frequency, and again, the same imaginary I. So this property is a vector, so it contains three components in Cartesian coordinates x, y, and z, unlike the pressure, which is a scalar. And this unit meters per second. This is not a speed with which sound travels, it's the speed with which particles of fluid or air oscillate when sound wave disturbs them from equilibrium. So also like with the pressure for a harmonic sound wave in elastic medium, one component of the acoustic velocity is a function of time, frequency, space, and the wave number. It is complex as well, and the complex value of the spectral amplitude can be written here. Okay, so why do I tell you all about this? Actually, it is because we use these quantities, P and U, so to define something which is very useful for acoustics of porous media. And this quantity is called characteristic acoustic impedance. So when I talk about quantity with a little tilde, I say this is spectral amplitude. So basically, if I take spectral amplitude of the sound pressure and divide by the spectral amplitude of the particle acoustic velocity, then I get a quantity which is called acoustical impedance. And this acoustical impedance, a complex quantity. It has real part and imaginary part. And real part in acoustical impedance is mainly to do with the propagating sound wave, or kind of energy propagates in space. Whereas the imaginary part is something which is actually sloshing around in normally porous layer, or something to do with the attenuation or not propagation. The unit of this quantity is pascals times second divided by meter minus 1. And this quantity is usually measured or predicted for a range of porous materials, and can be amazingly useful because it determines, for example, in noise control applications, how good materials are able to absorb sound, or it can be used to determine characteristics of porous media, which from acoustical data, which are hard to determine otherwise. Okay, so now then, the question is actually, what are the key non-acoustical parameters porous media which control, say, acoustical impedance and wave number? Okay, let us look at a very simple example. So this is actually a photograph of a typical porous material. This porous material, as a matter of fact, one of my students produced in the lab. And if you look at it, it's like bread, like sort of a cheese, which contains of pores. And when sound energy hits this material, it tends to go into the pores. And when it gets to the pores, the sound pressure and particle velocity, so it gets into the pores, and in the pores it tends to slow down and attenuate because it experiences resistance due to viscous and inertial effect in the pores. Also, some of the sound energy is lost because of thermal effects. The sound wave basically slows down, attenuates, and it happens in each of the pores in the whole material in here. Okay, so interestingly here, so the most important quantities here would be obviously the size of the pores and the number of pores per unit area, or porosity. And that's something which is actually, I'll show you on the next slide. So the key four properties, fundamental properties, will be the porosity of these materials, tortuosity, or actually how twisted the material pore is, or how uneven it is as a function of depth into the material. Also, a property like a pore size, or some characteristic of the pore size. And then another property could be variation in the pore size. So how much do the pore size vary? So by the way, here I'll just have a link to the website. I see if it works. Hopefully it does. So it contains a list of applications which you may want to read in your leisure time. Okay. Can you see it on your screen? Okay. Can you see it on the screen,
Yep.
guys? Okay, good.
Yep.
Good. Okay. Any questions so far? Any questions from anybody?
Nope.
Okay, good. So now then, so how do we move from these parameters to acoustical properties, which can be useful for all kind of applications? That's a good question. So there are very many models which can actually link these parameters to acoustic impedance and the wave number. What I suggest you do in your leisure time, you go to the website, which is set up by a company called Matilis in France. And this website is a Klondike of different bits of information about different models. So we see, for example, in here, the propagation models about, let me just see. Okay, so propagation models, which is when the material skeleton is not moving with the sound, which is a case I'm going to consider today. There are some models like Delany-Bosley models, Delany-Bosley-Mickey, Johnson-Champolat, and so on. This slide is with the active link. If you click on it again, so it should actually take us to the website again, and do go to look at it. It's really a brilliant website in my view. Okay. Now then, let's go back again. So let me talk a little bit about how normally these models actually convert non-acoustic parameters of those pores into acoustical properties. Mostly common what they do really. So they say, okay, well, let us define the density of the fluid in each of those pores, and let us define the equivalent bulk modules of the fluid in these pores. And if we multiply these two and take square root of it, so we can predict the characteristic acoustic impedance. Okay. So also they say, okay, well, if we know the density of fluid in this pore, and we know the bulk modules of fluid in the pore, and we divide density by the bulk module and multiply by the frequency, we can obtain the wave number. Okay, and these properties are obviously inherently complex. So, and they're all frequency dependent. So, and the frequency dependence is very interesting as well. So we can define two frequencies to understand better how these materials work. So we can define a so-called biofrequency, or viscous characteristic frequency, which is normally associated with a complex density, which accounts for viscous and inertial effects in the material pores. Okay, and it's this viscous characteristic frequency is quite important parameter because it separates two different regimes. So on one hand, there is a low frequency regime for frequencies which is less than this frequency, and this is a regime where viscous losses are dominant. So the friction on the pore walls is dominant mechanism of which determine propagation of sound. Also, there is a high frequency regime when frequency is much higher than characteristic frequency, and this is to do with inertial regime. So basically, when the mass of air trapped in these pores become important. And by the way, around this frequency, the thickness of the boundary layer, viscous boundary layer, is comparable to the pore size. So, and in this actually one frequency of sound close to this one, so the viscous friction and inertial forces are maximum in terms of the ability of the sound to attenuate. So effectively, in this case, the density, dynamic density of fluid in the pore is a function of the frequency of sound, porosity, pore size, and the variability in the pore size in here. Okay. Another frequency is the I don't know why it's animated. Anyway, another frequency here is the thermal characteristic frequency, and this is to do with the thermal exchanges. So when the frequency is relatively low, then we are in either thermal regime, and basically, so temperature, thermal energy can flow from hot areas where the sound wave cause compression to cold areas where sound wave cause rarefaction. And this is either thermal regime. When the frequency of sound is relatively high, it's adiabatic regime, and that's where thermal exchanges are negligible. By the way, this frequency determines the frequency of sounds for which the thermal exchange is most important in terms of the attenuation, slowing down of sound wave. By the way, what I didn't say, actually, these two frequencies are inversely proportional to the pore size. And they are proportional with the exponent of the standard deviation in the pore size. Also, this frequency controls the bulk modules, and which become function of frequency, porosity, mean pore size, and standard deviation of the pore size. Okay. By the way, in those slides which I showed you, so it's I've got a few variables, parameters. Eta is dynamic viscosity of air in pascals times second. Kappa is thermal conductivity of air, and Cp is heat capacity in air. Okay, so how do we predict acoustic properties in practical applications? Well, basically we say, okay, well, let's assume that that plane wave I showed you on one of the early slides, incident on the porous layer. And the porous layer has a thickness H, and it has impedance, characteristic impedance ZP, and wave number KP. Part of the sound energy reflects, part propagates, attenuates, and reflects back from the end, and part of this transmitted. So this will be reflection coefficient, there'll be transmission coefficient, and there'll be absorption coefficient. And it goes from medium 1 to medium 2. So this is basic equation which links the characteristic impedance of the porous medium. So with the impedance of the backing medium, and wave number in porous medium, and thickness of porous medium. If the backing medium is rigid wall, in this case, everything just simplifies to this expression, where basically the surface impedance of this porous layer attached to hard wall or rigid wall is product of the characteristic impedance of this layer multiplied by cotangent, hyperbolic cotangent of this quantity. Okay. And that, by the way, that's constitute the majority of cases in studies of the porous media. When we want to measure the properties of porous media or understand how it works in situ. In some cases, the sound is not incident at a normal angle of incidence. It's incident at an angle theta. In this case, sound will refract as it goes into the porous medium, reflects from the hard wall, comes back again, and refracts again. In this case, we say that's the same impedance, surface impedance, is also a function of the cosine of the refracted angle theta p. And the refraction angle is determined from the Snell's law, where we have a sound speed in porous medium divided by sound speed in air and multiply by the cosine of the incident angle. And that's really quite a common case in noise control because sound rarely incident at a normal incidence. So therefore, we need to consider what happens when this is the case. Anyway, any questions so far, guys? Anybody want to raise a hand and ask me something? Hello?
No questions so far.
No questions so far. Okay.
No question. Thank you.
Okay, good guys, good. Okay, all right. Well, now then, let's just see if okay, yeah. Okay, so in another quantity which we want to know very often is the absorption coefficient, and that's normally we need to know it for noise control applications. And the absorption coefficient is a function of the reflection coefficient, which is complex, or the impedance, surface impedance of the material layer. Okay. By the way, this quantity is real. It's not a complex absorption coefficient, whereas the reflection coefficient and the surface impedance are complex. Okay. How do we deal with the case when the sound incident on material at a plurality of directions? So when it's diffused field. We can either just use the previous expression and integrate over plurality of angles, or we can assume that some materials are locally reacting. In this case, we can use good old formula produced in 1950 by London, and it's published in JASA, which is actually, by the way, it's one of the active links you can explore. And it's a nice paper to read. It basically shows how in simple way we can predict the diffused field absorption coefficient from the measurement of a impedance in the impedance tube, okay, or absorption coefficient in the impedance tube. Anyway, I'll leave you to explore it in your leisure time. But basically, in this case, you've got a bit of a strange function of log of something which is called equivalent impedance, and the equivalent impedance is strangely is a function of the absorption coefficient for the normal incident case, which can be measured in the impedance tube. And this quantity this time is real. Okay, so all the typical effects of the or the diffused field incidence on the porous layer is illustrated here. So here we show absorption coefficient. It's a function of frequency for two cases. The red line is the normal incidence absorption coefficient, and the blue line is diffused. Generally, you've got a considerable increase, maybe 10-20% increase in the absorption coefficient for a diffused case. By the way, this actually calculation has been done for 25mm thick, hardback, highly resistive porous layer, which I discuss in a minute. Okay, now then, how do we choose a model? Okay, so I did mention on my previous slides there are a plurality of models, but how do we choose the right one? Okay, let's talk about that. So what I'm gonna do, actually, I just give you my own choice. Okay, so you're welcome to go to the Matilis website and look at the plurality of models. Also, there is a paper which I saved for you to read in that folder. This paper is my presentation in 2006 for the Tyndall Medal ceremony. And also there is a paper in International Journal of Acoustical Vibration, which describes all kind of models for all kind of applications. But today I give you my personal choice for those models which I think worthwhile to use. And I think there are 3 models which are worthwhile to use. Obviously, the first, my personal first choice is the model I developed in collaboration with my colleagues in Le Mans in France. And this model is basically 3-parameter analytical model, which predicts dynamic density, bulk modules, characteristic impedance, and the wave number in porous medium of any type, based on 3 parameters, which is porosity, mean pore size, and variation in the pore size. It's very simple to use model. It is causal, which is important. So it means actually that the real imaginary parts are linked with the Kramers-Kronig relations. So it doesn't predict nonsense. And it can be used for foams, granular media, fibrous media, and so on. What's nice about this model, I believe, actually, that's all these parameters are directly measurable. So the porosity is easy to measure, pore size is easy to measure, and standard deviation pore size is also easy to measure, which is good. My second choice is a very simple model which was developed in 1990 by Mickey, and that's an improvement to model by Delaney and Bosley. This model requires 2 directly measurable parameters, which is porosity and flow resistivity. Please do not confuse sigma with sigma s, which I use for pore size distribution. And it also requires 1 parameter, which is tortuosity, which is not directly measurable. But what's nice about this model, actually, it's very simple to use. And by the way, I saved a MATLAB copy of code to run this model in that folder I showed you before. You can play with it. This model doesn't predict dynamic density and bulk modules, but it predicts directly the characteristic impedance and the wave number. It also works for all type of porous media, but it's not causal. As the frequency of sound decreases, the model can give very peculiar results. So basically, the real imaginary part not properly linked, although attempt was made to do so. But it's quite robust. It's semi-empirical, by the way. It's not a analytical model. It's semi-empirical based on data. And the last model, which I think is actually very good, is the model originally developed by Champeau and Allard, and developed further by Lafarge. And often it's called Johnson, Champeau, Allard, Lafarge model. It predicts acoustical properties which match almost exactly those which can be predicted by the model, which is my first choice, almost exactly. But the difficulty with this model, actually, that's and it requires 6 parameters instead of 3, 6 parameters. And some of these parameters are difficult or impossible to measure. So the only parameters here which you can actually estimate is the porosity and flow resistivity, viscous flow resistivity. The other parameters are very difficult to measure, and they're not independent. They're all linked. So, for example, you can say viscous flow resistivity inversely proportional to the viscous characteristic lengths. Thermal flow resistivity inversely proportional to thermal characteristic lengths. Viscous characteristic length is proportional to the mean pore size and this quantity, and thermal characteristic length proportional mean pore size times this quantity. And tortuosity is also not independent; it's proportional to this quantity, basically, which is controlled by the standard deviation in the pore size. But it's causal. It works very well for all kinds of materials, and I'll show you examples later on. But again, the problem is some of the parameters are interlinked and they're very hard to measure. Okay, a couple of slides, or 3 slides, or 4 slides actually. It's about influence of the various non-acoustical parameters on the acoustic absorption. So what happens when we change one parameter and fix the others? Let's have a look. Let's say, for example, we have a 25 mil thick hardback, highly resistive porous layer, which is quite typical absorber used in high-end applications. It's not massively porous. It's only 0.8% porosity. So no, sorry, on 80% porosity. The flow resistivity is 150 kilopascal second meter minus 2. It corresponds to the pore size, which is about 60 micrometers. Tortuosity is about 225, and standard deviation, the pore size 0.3. So I use the model I developed in 2016, which is very similar to the one I described on a couple of previous slides to illustrate the effect. Let's freeze 3 parameters and vary 1. Let's say what happens here when we change the porosity. So when porosity is very low, only 10%, the quarter wavelength resonance dominates the behavior. So basically, it resonates at certain frequency, and it's not very good absorber at other frequencies. It's very hard for sound to get in the material because the most of the surface are not pores. When porosity is 1, so then it can reach the theoretical limits, which depends on the pore size. In another slide, I'll show you the effect of changing the flow resistivity or the pore size. So when the flow resistivity is high or the pore size is small, then almost no resonances actually occur. So basically, it's highly resistive layer, and sound enters the pores and very quickly attenuates. So it doesn't actually develop quarter wavelength resonance. When porosity reduces and pore size increases, this is typical for melamine foam. So the resonance develops and anti-resonance develops. And in this case, the sound actually can propagate to the hard backing and come back again to interfere with the incidence. One question came is actually that whether I take into account the elastic effects of the frame, not in this presentation. So as a matter of fact, there is a really nice model to account for this, and the nice software which I mentioned in the end, it is called AlphaCell, and that can take into account the frame effects. But in my view, the frame effects for airborne sound case are not very important unless you excite physically or mechanically the frame. So like, for example, in the case of sandwich panel. And that's actually the topic of a presentation by people from Matalis, which will come in a couple of weeks' time. Okay, let's look at the effect of changing the tortuosity. Basically, tortuosity, all it does is slows down the incident wave in the material. So as a result, the quarter wavelength resonance peak moves towards the low frequency, goes in here with the so it goes in here with the increased tortuosity, and less sound energy is able to enter the porous layer. The last slide is the effect of changing the standard deviation, the pore size. Increased standard deviation, the pore size, so from 0 to 1, results in a higher variation in the pore diameter. So therefore, higher surface impedance and higher resistance to the incident sound wave. As a result, the absorption coefficient begin to drop. Okay, how do we test these materials? There are a few methods, and to be honest, actually, maybe I'll just show you briefly. So there is a 2 microphone impedance tube method, which is standard. There is a 3 microphone impedance tube method, which is non-standard, but described in this publication, and it enables to measure not only acoustic impedance and absorption reflection coefficients, but also the characteristic impedance and complex wave number. Another method is 4-microphone impedance tube method. It's not a standard, but I described in this publication, and it also enables to measure all set of characteristics. Also, we can measure 2 more non-acoustical parameters using standards. One is the flow resistivity, which is measured by using ISO 9053 1991. It is being revised now. And the other one is to measure the porosity. Porosity can be measured using reasonably complicated BET techniques or techniques based on mercury injection technique, but also it can measure it using the method described in this publication based on the measurement in 2 sealed volumes. Okay, but most common way to deduce non-acoustical properties of porous media is to use inversion or have a guess. Well, somebody sent a mail saying actually revision was published in 2018 to the ISO 9053. Francois Xavier, I didn't know that. Thank you, Francois. Anyway, when we don't want to measure something, or we just can't measure it, so in this case we can use inversion technique, which is basically find out the difference between the experimentally measured quantity, which is frequency dependent, and the quantity which is predicted. So here we've got frequencies of sound at which this quantity has been measured, and we have a vector which contains our parameters, whether it's 3 parameter or 6 parameter and so on. And you can learn more about how to do it actually in this publication. But I'll show you some of the results. So some of the results which is published reasonably recently. So let's say, for example, we'll take a common material like melamine foam. I'll show you the picture of this material here. So we put this in impedance tube, 2-microphone impedance tube, and measure the real, which is blue circles, and imaginary, which are red triangles, parts of the normalized surface impedance. And then we run simulation to fit the parameters in the model. The model I developed with my colleagues in France, and the Johnson Shampoo Allard Lafarge model. And we find actually that the fit is really, really good. It's within a few percent across the whole frequency range in which we measure. So also we find that the 2 models, they're almost identical. So the only difference is one model takes 6 parameters, the other model takes only 3 parameters. And we find actually the parameters we had to feed in this model make sense. For example, the mean pore size is 115 micron, which is very similar to that you can predict by getting material data from the manufacturer. Porosity of the material close to 1, which you expect, because melamine foam is amazingly light. And to be honest, porosity doesn't really make much difference on the prediction as long as it's high enough. And the standard deviation pore size is quite small, which means that the tortuosity is quite low. And this is done for 16.5 milliliter melamine foam, which is a very standard material used in noise control applications. We also can show a similar figure, which is a comparison, the same comparison but for 21.5 mil thick layer of automotive felt. And this material used to line car boots and saloons to reduce noise. Similarly, the prediction, which is the circles and triangles, is very close to the data, and the 2 models almost identical. So it's reasonably high porosity, because it's not a dominant parameter, higher than the previous mean pore size, and a high standard deviation because it's full of non-uniform fibers. But the fit is within a few percent. Finally, I'll show you an example of the material, which is quite strange for noise control applications. Basically glass beads, loose glass beads, 40 mil layer of those loose glass beads. Similar comparison, surface impedance, real imaginary part against frequency. The reason why we use the glass beads because it's a very, very well defined material, which properties are well known and characterized with the non-acoustical means. For example, with the flow conductivity or electrical conductivity experiments. And when you look actually at the parameters which we have to fit in these models, they make really good sense. 300 micron pore size, porosity almost bang on for hexagonal packing, and standard deviation very similar to the one you can measure. Okay, so well, the data which I showed you here actually been obtained with the standard 2 microphone impedance tube, and I'll save you these. I'll show you this data where they are. These data are in this folder. You can access yourself and play with them. These are the data. Also, this contains MATLAB code, which you're welcome to run. And I'll show you briefly what does MATLAB code basically do. So you sort of choose glass beads code to plot. It calculates the best parameters which fit the data and plot them as a function of frequency against data, calculates more parameters for the Johnson-Champois-Allard-Lafarge model, call this model, and plots the whole lot. I'll show you an example of that. I think my computer is a bit slow because of the internet stuff. So it's going to come in a minute. Okay, so that's the result. The same result I showed you on the previous slides. You're welcome to play with this code and tell me what you think. So apply it to a range of materials you may have data for. It's an open source code. Okay, so what else I need to tell you before I shut up? So I need to tell you actually there are models which can predict the acoustical properties of porous media very well. These models are good to design good absorption material for noise control applications and also to study porous media microstructure acoustically. In many cases, there are no justification for the use of models with more than 3 non-acoustical parameters to predict acoustical properties accurately. There is a spelling mistake. And also there are commercial packages which can be used to apply this model to predict acoustical behavior of these materials and layered materials. And one particular package I can recommend you was developed by a very clever bunch called Matilis. And this is a link to this package. It's called AlphaCell. It's now part of Altair Alliance software. And it can do a lot of very interesting things for you. So, but it can also use the models which I presented you in my slides. Okay, so the other part of my presentation I'm not going to cover, so you can actually look at it yourself. It just basically tells you about ways to enhance product absorption. Okay, I'll stop here and I'll take questions now. Okay. Anybody has questions? Okay, I must have made everything very clear to you guys. So do you know where to find these codes, guys? So you got a link. How do you practically measure? Yeah, there is a question actually. So how do you practically measure parameters? Do you mean parameters of non-acoustic parameters or acoustic parameters? Okay, yeah, standard deviation in mean pore size. It depends on the material very much. So for example, if you have let's say, for example, if you have glass beads, so there are several ways to measure the standard deviation in pore size and mean pore size, because the identical glass beads for given packing, they would produce very well-defined pore structure, and then you can actually use theoretical model to calculate these properties. And that's why I use glass beads. So also you can use apply experiments which is to do with the water suction. You can, for example, take a sample of material, like say glass beads again, and saturate with water, and then apply suction pressure in steps to extract water. And the suction pressure is inversely proportional to the pore size. So therefore, you would know what would be proportion of pores of different parameters, size and radius, for example. So from the suction pressure data. So there is a paper I can send you a link to, or put in this folder you can read about. So also you can use more fancy stuff, like for example BET method, which is expensive thing based on adsorption techniques, or you can just guess. For example, in the case of the melamine foam, you can look at optical images, or manufacturer tend to give you data, like for example cells per inch, so you can calculate that. And if, for example, if you take this material and calculate cells per inch, you'll get 120. So we get 115 micrometers, which is very close. Okay. Did I answer your question, Ignacio?
Yes, thank you. I don't know if you hear me.
Yeah, I can hear you. Thank you.
Good. Yes, thanks.
So much has been done on porous materials. What do you think of the next step for these materials? I personally believe that there is a nice area to extend this study, which goes into nanopores, because the physics is very different in the case of nanopores. It's nice to develop a multi-scale model, which takes us from the classical sort of fluid and thermodynamics in micron plus pores to the kind of Knudsen stuff and molecular dynamics, which is in micron below micron pores. And that hasn't been done properly to the best of my knowledge yet. There have been people like Olga Umnova and what's his name, guys? Rodolfo Venegas. So who developed models, but they tend to have too many parameters, and they're not truly multi-scale in terms of actually applied to materials which pore size is distributed in a certain range. So in terms of the porous media, I don't know. Maybe characterization of materials, maybe developing something which is better measurement techniques. So for materials which are more complicated. So and for materials or techniques which are more reproducible. But otherwise, I don't know really. So I think it's too much been done. Francois, the extension of your parameters. Francois Xavier Bicot asking, can you see an extension of your parameter model to multi-scale materials? You mean, for example, to nanoporous media, Francois Xavier? Yeah. Well, yes, the physics will be different, but we use the PAD approximation, which is nice to use because it brings together low and high frequency regimes. The reason I started my presentation with the viscous and thermal characteristic frequencies, because these frequencies separate low high frequency regimes, and in the middle the behavior is a bit complex. So using some like a pod approximation is good because you can nicely, smoothly integrate these two. So extending that to nanoporous media where physics is quite different will be a good way of using it. But I don't have time or money to do it. Maybe some of you guys can do it better. Also, Francois Xavier said that the ratio of viscous resistivity to thermal resistivity is a function of pore size standard deviation only. It seems unexpected. Can you comment about it? My view, if you look at our publications in GIASA from 2016 and 2019, we show from the first principle that for a material which can be described by a analytical pore size distribution, so these non-acoustical parameters, which is thermal resistivity and viscous resistivity, are not independent. So they link to the larger and smaller scale of the pore size. So therefore, I think they can be linked via something like standard deviation in the pore size. And that's what we showed basically. If the standard in the pore size distribution in the porous media is log normal, it effectively just a ratio of approximately 3 times or something like that. So they're not independent. I don't know if I answered this question, Francois Xavier. I don't want to go into equations now, so you don't mind. But
Yeah, thank you for the
it,
answer. It makes sense. Thanks.
You probably see it here. You see actually it's this is the thermal permeability, and this is sorry, this is viscous permeability. This is thermal permeability. These are the same expressions, okay, but these are different. So if you find the ratio between them, so it'll be like a exponent to the power 6 times this bracket. So if you put, for example, sigma equal 0.3, so then it'll be about 3 times apart. So, and then you can see actually in you can see in the presentation. So, in this MATLAB code, where it is actually. So I'll just show you again on the screen. See the Johnson-Champollard model and this 3-parameter model. They almost identical. So it means actually the models actually show exactly the same behavior.
Yeah, that makes sense. Thank you very much for your answer. I mean, it's very detailed.
Well,
Yeah, thanks.
Thank you for attending, Francois Xavier. Lovely to hear your voice. I can't see you, but lovely to hear your voice. Yeah. So what the point I'm trying to, the point, because I'm an engineer, guys. Okay. So a point I'm trying to make actually. So if you can get away with the model, which is simple, so why use complicated stuff? And also, for example, in other applications, like say chemical engineering, when you want to measure, say, pore size from acoustical data for quality control or something else, you can use very simple model and which links directly to the pore size. Anything else? Well, talking about maybe future research, guys. Well, I think what nice to do if you look at what's been done in terms of the improving acoustic absorption of materials. I just found actually I can briefly show you, for example, like double porosity, which is nice, which is a thin resistive layer, including nanofibers, nice. Cavities, nice. We can call it metamaterials. Don't hit me on the head with this. For example, you can look at inclusions. Resonators again. So things like that. Maybe something else. Maybe something else he can come up, but I don't know really. I'm run out of steam on the classical porous media, guys. Okay. So in this case, if you have any questions, you know my email address. I'll stick it right in there. Yeah, in here. So you're welcome to send me questions. And I'm very happy to talk to you. If you decide, some of you, for example, thinking of putting grant proposal or something like that, we're more than happy to talk to you guys. I'm not going to steal your ideas because it's not something I working actively now. I've got a couple of PhD students, but I'm very happy to give you balanced advice, what I think is novel and maybe significant. What are the gaps in the knowledge this area of science may still have to answer? And if you want to know what model to use for your application, so you're welcome to talk to me. But if you really want to use it for something which is not so much, how to say, development, new theory and all the rest, just want to predict it, the best way to do is to use software. And I gave you a link to AlphaCell, which is wonderful software to use. Okay. Right, in this case, I'll stop recording now. Oh, somebody asking questions. Right, guys, thank you so much. Thank you. So good. You stay safe and enjoy your weekend. So, and I'll hope to see you soon in person somewhere or at another webinar. So do suggest webinars and do step forward to give webinars yourself. Okay.